So we've got a few more definitions here in this lecture. And the next one I want to talk about is this idea of cardinality or cardinal number. And this is another one of those things, math people, we just couldn't use size, for example, because that's really all this is, right? The cardinality of a set is just another way of saying the size of the set. And we do have a special way of writing that, right? If A is a set, then n of A, I think n for number, right? N of A is its cardinality, is its size. So let's look at some examples here. Right, I have this set A, the integers between 1 and 7. What is n of A? How many numbers are there in that set? Well, I'm going to count them up, right? We're only doing integers now, so it's going to be 1, 2, 3, 4, 5, 6, 7. 7 numbers on that list, so that's the cardinality. All right, so how about B? What is the cardinality of B? Well, positive even numbers. This is an unbounded set, right? There is no biggest number on this list. So this is an infinite. Having spelling issues today. Infinite. There we go. All right. So how about C? The set of all dogs. Well, this one is tricky. I know that it's finite. I know there are an infinite number of dogs in the world, right? But I still don't know how many, right? So, and again, that's going to happen. Sometimes we can't be any more specific than that. All right, so how about D? This is my weird set from the last slide. Well, remember what we talked about. What are the elements of D? This set is an element. This set is an element. And this set is an element. There are 3 things in that set. It has 3 elements. So that is the cardinality. All right, and how about the last one? What is the size of the empty set? Remember I said the empty set is the set with no elements. There's nothing in it. Right? So the cardinality of the empty set will be just 0. Okay, so now we need a way to compare sets. Right? We have 2 ways of doing this. 2 sets are equal if they have exactly the same members, if the lists, if you will, are identical. On the other hand, sometimes I'm really just concerned about sets of a certain size. Right? And that's where this idea of equivalent comes in. 2 sets are equivalent if they have the same cardinality, they have the same number of elements regardless of what those elements are. Right, so let's look at some examples. Right? And let's start by thinking about the cardinality of these sets. Okay, so the cardinality of A, we talked about this one a couple slides back. The cardinality of A is 7. The cardinality of B, well, it's got 3 letters in it, right? So the cardinality of B is 3. The cardinality of C, well, let's look at what this is saying. First, this is saying X has to be an integer, right? It has to come from that set Z, and it has to be between 1 and 7. Well, how many numbers are there? How many integers are there between 1 and 7? You count them up if you like. That's going to come out to 7. The cardinality of D, we actually talked about this one on the last slide. This is 2 slides back. And the cardinality of E is 0. Okay, so what can I say here? I can say that A and C are equivalent because they both have the same size. I could also say that B and D are equivalent, again, because they have the same size. Okay, and then now to talk about equal, this is a convenient first step, because if the 2 sets, if we're talking about finite sets here, right? If the 2 sets aren't the same size, then there's no way they can have the same number of elements, right? One is going to have more or less than the other. So let's look at B and D. Are these 2 equal? Well, if I look at B, X is an element of B, but X is not and D, right? So B and D are not equal because while they have the same size, they're made up of different elements. All right, so how about A and D? Well, A is the numbers 1, 2, 3 up to 7. And C is also the numbers 1, 2, 3 up to 7. So not only do they have the same size, they have exactly the same list of elements, right? Which means A and C are equal. You notice I use the equal and not equal. Right? We're not going to try to invent some new symbol for it. We're going to use the same symbols you're used to for those ideas. Okay, so how about this idea of a complement? Think of a complement as being like the word not. Right? So the complement of A, right? Here's how I'm going to write this. There's a couple different ways this is written. You'll see this written A with a little apostrophe. You'll see it written A with a little C. And sometimes you'll see it written A with a bar over it. They all mean the same thing. All right? I'm going to try to stick to writing that A apostrophe one because it's just the one I'm most used to. What this means is this is the complement of A, and in practical terms, this means everything not in A. Well, to talk about things that aren't in A, first I have to know what constitutes everything, right? And that's where this idea of the universal set comes in. The universal set tells me what everything is. Right, so if I want to talk about the situation here, right, I want to know what is the complement of A. Well, I'm going to go to my universal set. That's my everything set, and I'm going to cross off everything that's in A. A is just the even numbers, right? 2, 4, 6, 8, and 10. So if I cross off 2, 4, 6, 8, and 10, what's left is the complement of A. 1, 3, 5, 7. And 9, right? That's how you do a complement. Okay, so why don't you take the next one here? See if you can kind of go through that same sort of process, figure out what the complement of B is. Well, I'm going to do the same thing. I'm going to cross off 1, 2, 3, 4, and 10, and everything that's left, 5, 6, 7, 8, and 9, that is the complement of B.